Hello everyone. Today we will be discussing grammar and Chomsky hierarchy. Uh, that is a concept under theory of computation. So we'll be discussing different type of grammars that are under the Chomsky hierarchy. So before we proceed to grammars, we will have a look at languages and grammars. Now, basically, grammars are associated with languages. So, language is basically a collection of sentences of finite length. Now, for example, as shown on the slide here, we see that this is a binary language. So, binary because there are only two allowed symbols in this language, and hence the alphabet set here contains only 0 and 1. Now, using the 0 and 1, we can form different strings, and these strings together are called as sentences, and a set of these sentences is called as a language. So this is a formal language. The languages which we will be talking about in this will be formal languages and natural languages. So, English is a natural language wherein whatever we speak, whether it is correct or incorrect, can be uh, found using the grammars. So, these grammars are nothing but set of rules which define how a language should be constructed. So we know that when we when we write or speak in English, we need to follow certain sequence. So we'll be having a look at smaller grammars to understand how do they allow us to form a proper language. So for now, we know that it is a set of rules that help us to define proper language. Okay, so if we have a look at the example written here, so the example says the mouse wrote a poem. So if we look at whether this is a valid English sentence or not, it is basically a valid sentence because there is no grammatical mistake here. Now, since this is following a rule or it is following grammar, we say that it is correct. In terms of computer programming languages, we have been calling this as syntax of any language. However, there is another part to a language which is semantics. So, if we consider this sentence, probably it is not so correct, or it goes into Disneyland, which is possibly not correct for the real world. So, any formal language is specified by well-defined set of rules. Now, there are two key questions. So, the first one is a combination of words a valid sentence? And then, how can we generate the sentence for a formal language? So, to address these, we will be looking at grammars. Okay, so let us talk about a sample grammar. Now, basically, before we start discussing about grammar, let us discuss two important terminologies. One is non-terminal and the other is terminal. Now, whenever we write grammars, we will be using a few symbols or maybe alphabets to denote the grammar. So to denote any grammar, we have a few symbols on the left arrow and a few symbols on the right. Now, non-terminals are basically those which can be expanded, and terminals are basically the unit symbols or the ones which cannot be expanded. Okay, so having said that, let us take a small sample grammar. So I write S. This gives me some different uh, symbols here. And then these symbols themselves can be expanded. So let me just write this and then we'll see what are these symbols and what is this grammar all about. Okay, so here the first uh, symbol written here is, so maybe we can represent this whole grammar in the form of a tree that starts at S. And then this S is a non-terminal basically, which can be expanded. Now, how do I say it can be expanded? Because it has a rule, and this rule can be expanded to D, N, and V. So therefore, this S becomes a non-terminal. Now, if we see D, D also has two options for us. Obviously, we cannot expand using two options. Now, if I say two options here, it is the, and this vertical bar indicates or. So this D can be expanded using the word the or a. So let me just expand it using the word the. Okay, next comes up N. Now this D, since it was allowed to be expanded, it is a non-terminal. And this D is basically a vocabulary word in this language which cannot be expanded further. So this D comes under the terminal set. So we are also building these two sets and trying to see what this grammar is generating for us. Okay, now then we have this N. Now N can be expanded using either of these two words, cat or dog. Okay, so this cat, dog, since these are vocabulary words, cannot be further expanded, they will be in the terminal set. Maybe just expand it using dog. So the dog. Now the next one is V, which we can expand further using either of these two words. So the first one is runs and the other one is sleeps. So say we expand it using sleeps. So now using this grammar, we have generated one sentence, that is the dog sleeps. So this is one sentence of the language which we have constructed or found using this grammar. There can be a few more sentences that we can form. So we can have the cat sleeps. We can also have a dog sleeps. We can have a cat sleeps. So basically, all the different combinations of D, N, and V would be the valid sentences. Okay, so these are individual sentences. My language will contain all these sentences. But then this is a finite language because This grammar specifies only a few words in the vocabulary, and I can generate only a few sentences here. We can go about generating more sentences from these given words. So we can also have, say, the dog runs, the cat runs, a cat runs, a dog runs, and so on. So now this was a sample grammar which we took, and using this grammar, we have seen that we uh, could generate sentences for the language. So that is how we can frame rules, and those rules will help us to find out what all are the valid sentences for a language. So, for example, if we talk about high level languages like C, they do have these set of rules defined. So those set of rules we call them as syntax. So only if we follow the syntax correctly, we say that we have written the C program in a syntactically correct manner. So having the knowledge of what the grammars are and how do they help us to relate to language, we will now see what are the different types of grammars. So different type of grammars are defined in the Chomsky hierarchy. So basically there are four type of grammar according to this hierarchy: type 0, 1, 2, and 3. So this type 0, if you see, is the outermost set here, which means it is an unrestricted grammar. So since it is an unrestricted grammar, it basically allows us to have any combination of terminals and non-terminals, which obviously uh, will allow uh, a huge volume of sentences or languages. And this type 0, which is an unrestricted grammar, is corresponding to a language that is called as recursively enumerable language. So, the grammar which is unrestricted is used to form recursively enumerable language. We will be going in depth of all these in this subject ahead. And the type of machine which can be used to recognize such type of grammar is called as Turing machine, which also we will be studying in the due course of this subject. Now, imposing a few restrictions here, we have type 1 grammar, which is the context sensitive grammar. This context sensitive grammar accepts or recognizes the language which is called as context sensitive language, and it is accepted by linear bounded automata. The next type of or the type 2 is called as the context free grammar, and it helps us to recognize context free language. The last one here is type 3, which is regular grammar, which helps in the identification of regular language. And what we can use to recognize this is called as a finite automata. Now, all these concepts we will be going through in depth in this subject. Now, this was about the different types of grammars. We'll now one by one have a look at these grammars and see a few examples. So the first type is called as the unrestricted grammar. So as the term suggests, it is unrestricted. Uh, However, grammar rules have this format, something say alpha tends to beta. So here, alpha can be anything. Alpha can be anything, terminals or non-terminals. Similarly, beta can be anything, terminals or non-terminals. Now we can have any number of terminals, non-terminals in any combinations. We can have anything coming prior. So there is no sequence restriction. So that is why it is called as an unrestricted grammar. So let's just have a quick example here. So for example, this is one rule in this. So now if we say, let us assume that the capital letters which I am writing are non-terminals, and the small ones that I'll be writing will be terminals. So all these non-terminals could then be expanded further or have their rules defined. And the small or the terminals are the smallest unit and cannot be expanded further. So then if this is the language, it will obviously have rules for A, capital C, and B. Okay, but this satisfies the unrestricted grammar condition because here I have terminal which is allowed. Here I have terminal, this is non-terminal, non-terminal, one terminal, and again non-terminal. Now, since there is no restriction, we can write rules in any format. So this is also a valid rule here. We can have multiple uh, terminals or non-terminals this side in any sequence. So I can also have a terminal before the non-terminal here and any sequence on the right side as well. I can have any number of terminals, non-terminals on either side of this production rule. So all these are the example of unrestricted grammar. Let us now go to type 1 grammar, which is context sensitive grammar. Now, context sensitive grammar, obviously it is inside type 0. So all the type 0 would obviously be type 1. But here I have one restriction which is imposed. It says the in the production rule of the format alpha tends to beta, the left hand side or alpha, the length of alpha should be less than the length of beta. That is, we should have less number of symbols here than on the right side. Okay, so let us see a few examples. Also, one more thing, we cannot have alpha to be epsilon or it cannot be empty. Yeah, so let us see a few examples here. So this is allowed since it is any number and this is length 1 and this is length 3. So this is allowed. Maybe I can have something like this. Now this says it should be less than or equal to. So two symbols here and two here are allowed. However, there is no restriction on how terminals and non-terminals should be sequenced. So this is also a valid context-sensitive grammar rule. Next, I can have this side ACB, then maybe something like this. Now, this length is less than the length of the RHS, so this is also an allowed rule. I can also have a terminal followed by non-terminal this side, which is also allowed. So all these are valid symbols for or valid rules for the uh, context sensitive grammar. Say, for example, I have a rule like this. So if you see this length is 2 and this length is 1. in this case, it will not be allowed inside type 1 or will not be called as context sensitive grammar, although it will be a type 0 or unrestricted grammar, but it cannot be a context sensitive grammar. Let's go to the next type, which is context free grammar. Now, this is the most used type of grammar, or rather, the example which we saw in the initial video today was also this type of a grammar wherein I have shown how do we expand the grammar. So, this is the type 2 grammar or context free grammar. Uh, or we call it as CFG for short. Most of the programming languages use this type of grammar. The language which this generates is called as context-free language. Now again, since type 2 is contained inside type 1, which is inside type 0, obviously this type 2 needs to satisfy type 1, but additional condition is imposed. Now here the additional condition is that the length of the left hand side should be only one variable. Moreover, this should be a non-terminal. So if I say non-terminal, it should be expanded. I cannot have a terminal on the left hand side here. So we cannot have a terminal here. However, again, there is no restriction on the right hand side. So if we see this no restriction on the right hand side allow us to accommodate as much language as possible. And restricting the left hand side allows us to have proper expansion of the language while keeping track of what we have done so far. Okay, looking at a few examples of this context free grammar. So say S tends to A, B, C. Again, here there is no restriction to the terminals, non-terminals, and the sequence and the number they are coming. So this B can be only a small b, which is allowed. B can be B, S, B, C. It can be anything, any length, any number. It can be B tends to capital C. So the only restriction is on the left hand side, I need to have only one variable, which should be a non-terminal or which can be expanded further. Now, the last type of grammar is called as the regular grammar. So, this is the most restricted type of grammar because that is uh, the most inside the set. Type 3, type 2, then we had 1 and type 0. So, this is called as the regular grammar. Now here it says that we can have only one non-terminal because that was the condition of type 2. However, it now imposes restrictions on the beta side as well, and it says now I can have either a single terminal, so that is one thing, or I can have a single terminal followed by a single non-terminal. So here this is a terminal. Again, it is only one terminal is allowed, followed by a single non-terminal. So this is the most restrictive form which allows only these two type of production rules in the grammar. So anything which I am writing of this form alpha tends to beta is called as the production rule of the grammar, which is specifying some or the other condition in the language. Okay, let us just quickly have a look at the formal definition, or how formally we have to specify writing a grammar. So what we have seen up till now, just the production rules, or how we can specify a production rule. However, grammar comprises of more than production rules, and that is just a part of the entire grammar notation. Yeah, so we will be sticking to context-free grammar, wherein we said that it is alpha, beta, and here we can have only one non-terminal, and then this is anything and any combination of terminal, non-terminal. So we can define a grammar with the help of four symbols. First is V. V is a set of non-terminal symbols. Next is T, which is set of terminal symbols. S is the starting state. So we just saw writing the grammar rules, right? So the first non-terminal here generally is considered or to be written as the starting symbol. However, we can specify a different start symbol. And this P is the set of all the production rules which we write. So let us have a look at uh, a sample grammar here. So we have to define V, which will be set of non-terminals. Next is T, which is set of terminals. Next we have S, which is the start symbol, which will only be a single symbol. And then P is the set of production rules, where I'll be defining rules of the form alpha tends to beta, which we are writing in the CFG format. Okay, so let us write a few rules first. So S tends to maybe A, capital B, and D. Next, we have B and D here. So let us expand. So this is just an arbitrary grammar that I am writing. Maybe this gives me something like this, and this gives me this. Yeah. So these are my set of production rules, all in context free grammar type, because left hand side has only a single non-terminal and right hand side is allowed to have any number of terminals and non-terminals. Okay, so my starting symbol, or the symbol from where I would be starting building my tree or derivation or expansion, is S. So here I will write S. Now, since this is not a set, I can probably write only S. Then all the terminals which cannot be expanded further, obviously all the terminals are the ones which are not getting expanded, or those which are not specified on the left hand side. So the terminals of this language are small a, b, d, and e. Okay, and then we have non-terminals. So for non-terminals, all the symbols which are getting expanded will be my non-terminals. So we have S, B, D. So now this is the entire grammar notation, and not only this production rules which we have seen. So we specify grammar by this four V, T, P, and S. Non-terminals, set of non-terminals, terminal, set of terminals, production rules, and the starting symbol from where we should be starting.